All right, we're back with Math 676, and what I would like to talk about now is one of the really key points of deal.II, namely the use of adaptive meshes. So adaptive meshes refers to a technique where we want to use meshes that are finer in certain areas than in other areas. So we would like to have, for example, in corners a relatively fine mesh because we know that there is a singularity. And in areas where nothing is happening, we would like to have a coarse mesh. And so I would like to motivate a little bit how we get there, what the mathematics behind this is, why this works, and then show you a little bit about how you do this in practice. So traditionally, if you look at the error estimates that we have in mathematics, typically, let's say you want to solve the Laplace equation or a Poisson equation, and you want to use the usual Q1 or P1 elements. If you do this, then what you find is that the error in your solution, so the E is the difference between the exact solution and the discrete solution, that the error is bounded by a constant times the maximum mesh size times something like the second derivative of the solution, the norm of the second derivative of the solution. And because I will want to use this in the next slide, one of the equivalent formulations, of course, is if I just square both sides of this equation. So I'm going to take the square of the error, or the norm of the error in the h1 norm, less or equal than this constant squared h squared times the norm squared of the solution. So you might think that one way to deal with this then is, in order to make the error as small as possible, you would have to make the size of the largest cell as small as possible. So you would have to reduce the mesh size globally. And that seems to be the only thing that you can play with, right? Because the h2 norm of the exact solution, that is something that is given. There's nothing you can do about it. So that would suggest that the way to make the error as small as possible is by reducing the size of the largest cell. That means we have to refine the mesh globally. Every cell in the mesh has to be refined at one point or other. But so if you look at this a little bit closer from a mathematical viewpoint, and you go through the analysis of the error, what you find is that a sharper bound on the error is something like this. Namely, that the square of the h1 error, that's the thing that we have on the left here, is actually bounded by something like this, namely this constant squared, and then we have not just the maximum mesh size times the global h2 norm of this solution, but in fact something like a sum over all the cells k, so k are the cells of my mesh, times the diameter of this mesh squared, the diameter of the cell squared, times the h2 norm of the solution on this particular cell. So what this means is that in order to make the error as small as possible, one of the things that we should really be doing is not just make the mesh globally fine, but we should actually take a look at where it is necessary and make this h, this diameter of these cells, fine only where the second part of this factor here, namely the solution, has a large h2 norm. And so if you think about this, then how this should work, let's say we would want to make certain cells small and others we can leave large because the h2 norm there is relatively small. The question is then how should we balance these two things? If you ask the question how would we want to make the error as small as possible, subject to the constraint that the mesh remains as coarse as possible global, so that the number of unknowns is as small as possible, then it turns out that you can show that the best possible strategy is if we equilibrate the local contributions. So we want to make this factor h, the diameter of each of the cells, so that the contribution of every cell k, that's the thing that was under the sum, is roughly equal among all of the cells. That means we have to choose h in such a way that it is something like 1 over the h2 norm of the error. And you see immediately, for example, that in places where the solution is, we call this rough, so where it, for example, oscillates strongly, then the second derivatives of the solution are going to be large, and the norm of the second derivatives are going to be large. That's the places where we need to make h small. Whereas those places where the solution is more or less constant, for example, then the h2 norm of the solution is going to be very small, and we can choose a large mesh size. So in practice, of course, we don't know the exact solution. And in particular, we don't know the exact errors. So one of the things that you have to do in practice when you want to do this is that you have to come up with some sort of indicator for the error, right? So we have to compute, let's say, an approximation to the error or estimate the error somehow. And then our goal is to choose the mesh size in such a way that the error indicators are equilibrated. That means that all of this, roughly among all the cells, the error indicators have the approximate same size, and that the sum of these error indicators equal the tolerance to which we want to solve our equation. So let us call these indicators eta, and then the equation that we want to satisfy is we want to make h small enough so that the sum of the error indicators roughly equals the tolerance. So here's an example of how this should look. So if you look at the left side of this picture, this is a simulation done by a code called Aspect that we write that solves thermal convection. So you can think of this as the area between the Earth's core on the inside here and the Earth's crust on the outside. And you have, of course, the Earth's core being much hotter than the Earth's crust, so you have hot material rising up, just like in, let's say, a boiling pot. Hot material rising up in these very narrow plumes here. And then you've got cold material falling down from the surface, and then some background medium here. And you can easily imagine, of course, that in order to resolve these sort of plumes here, it's really only important to have the mesh fine where something is happening here. What we call this where something is happening. That means where the derivatives of the solution are large. Whereas if nothing is happening, like in this area here, we might as well choose a coarse mesh because we do not need all of these degrees of freedom to resolve the solution there. And of course, on the right side of this picture, you see exactly that this is what we do. So this is a mesh that we have generated with the help of refinement indicators or error indicators that show us where it is necessary to refine the mesh, to minimize the error. So these are the sort of meshes that we would like to do, or that we would like to create. And the process of doing this is called adaptive mesh refinement, and is often abbreviated AMR. So let's say this is what we want. And so let me talk about a little bit how you create these sort of meshes. So there are two fundamental observations. The first one is, except for very special cases, I cannot come up with these sort of meshes right away. And the reason is because if you look at this picture again, what you see, of course, is that while we have made the mesh fine in those areas where the solution has some activity here, where, for example, these plumes are rising up, but of course, a priori, before I even start this computation, I don't know where these places are. There's nothing that I can do to predict where I would have to have a fine mesh. This is something that the only way I can do this is that I can create this mesh after I have already solved the partial differential equation. And so the way this typically happens is that I can't create these meshes a priori, but I can do it iteratively. So I solve, for example, on a coarse mesh. I look at the solution, look at where something is happening. I evaluate my refinement indicators on this coarse mesh with the solution that I have computed on it. And based on this, I create the next finer mesh. And then I solve again there, and I look at the solution, compute error indicators, and I refine the mesh and solve again. And it seems like a really expensive process, except when you realize that, of course, every time I refine the mesh, I increase the number of degrees of freedom. And we strive, for example, to increase the number of degrees of freedom by a factor of 2. And that means that in the best case, the solution on the finer mesh costs me twice as much time as on the previous mesh. Now, on the previous mesh, it cost me twice as much time to solve than on the then previous mesh. So you see that the first few steps are essentially for free, right? They cost me an eighth, a quarter, 1/2 of the time to solve on the finest mesh. And that's why this method works. That's why I can do it iteratively, that I start out with something that doesn't cost me very much, and then eventually come to a point where the solution is accurate enough that I can say, okay, now I have reached my tolerance and I can terminate this iteration, because really only the last one counts. Of course, this whole process is more expensive than solving just once on this mesh, but if you go back one more time, if you think about this, then you will easily realize, of course, that the number of degrees of freedom that I have in this kind of mesh is far, far less than what I would have if I had globally refined this mesh to the same accuracy that I have along these filaments here, for example. So a rule of thumb is, for example, that in 2D I can save approximately a factor of 10 in the number of degrees of freedom, and in 3D approximately a factor of 100 to get the same resolution, because most of the time the solution is not globally rough. I can refine only in relatively small areas of the domain, and I can keep it coarse in other areas of the domain, and so as a consequence the total number of degrees of freedom is much smaller than it would be if I had a globally refined mesh. Let me show you ways how you can create these sort of meshes. So the basic algorithm, as I said, was you start with a coarse mesh, you solve on this mesh, then you compute an error indicator for every cell on this mesh based on the solution that you have just computed. For every cell you compute your error indicator, and if the sum of these error indicators is less than your tolerance, then you stop. Otherwise you mark a fraction of the cells, for example those with the largest error, and you refine the marked cells to get a new mesh, and then you start this whole process over again. And if you go to the literature, this whole process, this basic algorithm, is typically called solve, mark, refine cycle. And for reasons that I have never fully understood, everybody seems to be writing in capital letters. It might be a holdover from the time when everybody was programming in Fortran, where everything is written in capital letters, but this is how you typically find it in the literature. Okay, so what I would like to do is show you a little bit about the mechanics. How do you refine a mesh? How do you go from one mesh to the next mesh? And there are, for triangular meshes, there are essentially three relatively simple strategies, one of which that I'm not going to talk about very much, but the other two are a little bit algorithmic, and I would like to introduce you to this. So among these three methods are something that we could call de novo generation of a new non-uniform mesh. That means I look at my solution, I find these error indicators, and then I create a completely unrelated mesh with a mesh generator that is finer in those areas that I wanted to refine and equally coarse in the other areas. And you can do this because many mesh generation programs have the ability to take a function that for every point xy or xyz specifies a preferred mesh size. They will not be able to match this exactly, but typically what you can do is you can say, I would like the mesh to have a size of 0.1 in this area of the domain and a mesh size of 0.2 in that area. I'm not going to talk about this very much. This is sort of the old-fashioned way of doing it. So this comes from a time when the mesh handling software that we use in finite element codes was not equipped to refine meshes. This was, let's say, in the 80s and 90s. But today we have much better ways of handling meshes. And so I would like to go over the two most common methods for triangular meshes that are called longest edge refinement and red-green refinement. And I would like to state that so the same kind of process that I'm going to show you works also for tetrahedra in 3D, and that there are, of course, other strategies besides longest edge and red-green refinement as well. But these are let's say, the prototypical ones that you can think of. And so I'm going to show them in the next few slides. So let me give you an example. So let's say we have this mesh on the left, and we would like to refine this triangle that I have marked in red. So we've decided, for example, that the solution on this one cell is not accurate enough. The error indicator for this one cell is too large, and we need to refine it. So what we do is we're going to split this triangle into two smaller triangles. And we're going to do this by introducing a new vertex on the longest edge of this triangle. So the longest edge of this triangle is the one on the left. It's this one here. So we're going to introduce a new point on the middle here. And then we're going to run another edge from this point over here to the opposite vertex. So it's going to look like this. And then, of course, we don't have a mesh anymore that satisfies the typical properties that we always want from meshes, namely that every vertex is shared. So every vertex that would be here would also have to be a vertex of the triangle on the opposite side. But right now it isn't. And so what we will do is we're going to run this from this new vertex here, we're going to run a new edge all the way over to the opposite vertex. Okay, so it's going to look like this. And then we're done. We have a proper new triangulation that we can use. This has one drawback if this neighboring cell here had a different shape. So let me give you a variant of this mesh. So if this mesh had looked like this, for example, so I have pulled this vertex here that used to be here, I have pulled it all the way down. So if you think about what would happen if I run a new edge from this point here all the way to the opposite vertex of this neighboring triangle, then you get two slivers of triangles that are really not very well behaved. And we know that the error of the finite element solution becomes large if the triangles degenerate. So we get triangles that do not look very good here. So one of the things that we will do in these sort of cases is, instead of always unconditionally running a new edge from this new midpoint of this edge that we have refined all the way over to the opposite vertex, we're only going to do this if the edge that we have just refined is in fact the longest edge also of this neighboring cell. That's not the case for this one here. The longest edge of this neighboring cell is actually this one here. And so what we're going to do is we're going to run an edge from here to the midpoint of the opposite edge here, and then from there to the opposite vertex. So we have now refined this triangle here, this sliver of a triangle, into three smaller ones. And then we of course ended up with this additional vertex here, and this one we would like to either run across to this vertex if this here is the longest edge of this neighboring triangle, or we repeat this same process. In this case, the longest edge of this triangle is this one, so we're going to run it over here and then from there to the opposite vertex. So we get this kind of mesh, and you can see how this process potentially propagates, but hopefully eventually it will terminate. In any case, the process is of course designed in such a way that we avoid slivers of triangles that become finer and finer, or let's say more and more elongated. So if you analyze this algorithm, longest edge refinement is designed to keep triangles from degenerating. That's why we have these two steps where we decide where we want to run the new edge. It's not local. That means that if you want to refine one triangle, you will also have to refine the neighboring, but potentially the neighboring triangle of the neighbor, and so on and so forth. This whole set might propagate. So this is what I mean when I say that refinement is not local. And there's a statement that you can have degenerate situations where this is a runaway process. So the typical case looks like this. Let's say if I have a mesh like this, and I want to refine the topmost triangle. So here, I want to refine this one. The longest edge is the one at the bottom, so I need to introduce a new vertex here and add a new edge. But then, well, it turns out that the longest edge of the neighboring triangle is this one here, so I need to run an edge down here. So I have a new vertex on this edge. I need to run an edge from here to the longest side of the triangle beneath it that goes down here. And so what I get is a mesh that looks like this. So it turns out that I have refined every single triangle of this mesh only because I wanted to refine the topmost one. And you can relatively easily construct situations where this means I have to go through the entire mesh. This is of course a much smaller mesh than I care about in practice, but you can create cases where I have thousands or tens of thousands of cells, and I'm going to refine every single one of those. To make things worse is you can construct cases where this process never ends, where, let's say, the bottom triangle here somehow maps back to the topmost one, and when you're done with the bottommost one and all the cells that come around here, you have to refine this one again. So there's an infinite recursion. And there are variants of this method, of course, that avoid this. So typically what you have to do is you give up the property that you can never have a triangle that degenerates. You have to sometimes make that compromise, but at least you can terminate the recursion. So one of the things that people have done is they came up with an alternative strategy to this that is called red-green refinement. So let me show you how this works. We start with the same mesh again. We say again we want to refine this triangle, and so what we do is we mark every cell as red. So red is just a tag. We call these cells red, or green. It's just a tag that we attach to every cell. So we start with every cell being red. And then what I'm going to do is, if I refine this red cell here, the way I'm going to refine it, instead of cutting it into 2, I'm going to cut it into 4. Namely, I'm going to take the midpoints of all the edges, and I'm going to cut this into these 4 triangles. It turns out that they're all congruent to the original one. So you end up with triangles that are all exactly the same as the original one. And then I need to do something about these new points that I introduced here. And so I'm going to run an edge from every one of these points to the opposite vertex of these neighboring cells. So I'm going to bisect the neighboring cells, and these bisected cells I'm going to call green cells. So everything looks all right. I have 3 cells that have degenerated a little bit. Now, what if I wanted to, in the next step, refine this one, this cell here, for example? So let me take a look at this. When I want to do this, I need to refine this, because it was a red cell, into these 4 little ones. Okay, and I end up with this new vertex. And so the question is, what do I do with this new vertex here when the neighboring cell is green? Well, the answer in this case is, if I want to refine a green cell, what I'm going to do is I'm first going to merge the 2 green triangles again to get the original red triangle that was underneath here. And then I'm going to refine the underlying red triangle either into 2 green triangles like this, if that's possible, or because I already have a vertex over here, for example, I'm just going to refine it as a red triangle. So I get a mesh that looks like this, and for the cell up here, of course, I split this into 2 and I get a green triangle. So green triangles are second-class citizens. When I want to refine a green triangle, I merge it with the other green triangle, and then I'm going to refine it as a red one. So if you analyze this sort of method, you will find that it also keeps triangles from degenerating. In the worst case, you make it worse by a factor of 2, but you can never have a runaway effect of making these triangles worse and worse and worse into slivers. The process always terminates. So it always terminates after a finite number of steps, because well, if you hit a green triangle, you make it into a red, but the red one might at worst introduce 1 green one layer away. On the con side, of course, as I say, you refine this by a factor of 2, you make it worse by a factor of 2, and in particular, of course, it takes a lot more implementation effort to keep track which cells are red and which are green. Ultimately, I think today this is not that big a factor. We know how to write software for these sort of things, but that's one of the downsides for sure. So these are things that happen for triangles, and in deal.II, what you have seen, of course, in steps 1 through 4 is that all we do is quadrilaterals. And so what I would like to show you is how do you deal with this in the situation of quadrilaterals. So let's say you start out with the mesh at the top left, where you have just 4 quadrilaterals, and you want to refine the topmost one. So instead of refining it, for example, into 2 or 3 other quadrilaterals, I want to refine it into 4 by just bisecting it. Okay, so I'm going to take a cut in X direction and a cut in Y direction, and what you will find is that the 4 child cells have always better properties than the mother cell. That is true even if the mesh is deformed. In this case, of course, we have only squares. It doesn't matter. But if you have general quadrilaterals, the 4 child cells are always better. So I refined this one cell, and then the question is, what do I do with these neighboring cells? Because I still have this one node here that I have to do something with. And it turns out that there is no real easy option to do this with quadrilaterals. If I insist on the fact that all the cells in my mesh should be quadrilaterals, then I cannot come up with a reasonable strategy that would keep all of these cells as quadrilaterals and never have these sort of what we call hanging nodes on edges. So there's, of course, a few strategies in the literature, but nobody seems to be using them because they're just too complicated, or they don't work in practice, or they have degenerating quadrilaterals. So this is a real conundrum. It's not as easy for quadrilaterals as it is for triangles. And so the answer is, when you want to use quad meshes or hex meshes in 3D, essentially you have to find other ways to deal with the consequences. So you have to deal with hanging nodes. There is no way around it. And you have to find ways to make these hanging nodes go away, let's say, not on the level of the mesh, but on the level of the finite element space. And typically what we do this with is something that we call constraints. So when we introduce constraints, we take care of hanging nodes on an algebraic level, or let's say on a finite element space level, and we deal with them on the mesh level. It has additional advantages, namely that these sort of constraints that we get have other applications too. We use them, for example, when we have HP refinement, or when we use boundary conditions, and so on and so forth. We can deal with this in the same way as we do hanging nodes. So the approach to this is a little bit complicated, and I will devote the entire next lecture to the issue of how to deal with constraints. And then the lecture after that will show you how to actually use this in practice, and how. So for example, in step 6, that's the first program where we will use this, we'll demonstrate how the classes that are behind this will be used in practice. So in the next lecture then we'll come back to constraints.